guys, so let's start with sodium and let's see how you did. You tried this one on your own, okay? Let me ask you a question before we get started. How many total electrons does sodium have? 11, okay? And is that 11 number on the periodic table? Is that technically number of electrons? No, Ariana, what is it? It's the number of protons. It's called the atomic number. But if we're talking about a neutral atom, what else does it tell you? The number of electrons. Okay, so we're good. All right. And then why is there a certain order that we configure electrons in? Does anybody know what it has to do with?
The shells from the inside out.
Shells. Okay, what's another word for shells?
Layers.
Besides layers? Very good. Energy levels. And so now that we're in AP Chem, we need to graduate from calling them rings or shells to energy levels because it actually is all about the energy. Are we trying to give an element the highest energy it can get or the lowest energy? Actually, the lowest. In chemistry, everything is trying to get stable, and more stability is associated with low energy, okay? And sometimes, like in chemical reactions, there's actually several little things going on, right? There might be the loss of an electron, the addition of an electron, a Coulombic attraction. There's a lot of little things that go on, and when you add up all the energies of the processes in one big process, if you end up lowering your energy, then it's typically a process that will be spontaneous. It'll happen, okay? If you end up raising the whole energy of the system, it's typically something that you have to make happen. Does that make sense? So it's all about low energy. And it's not because we decided that. It's because as we were experimenting and measuring or calculating energies, we always found that things got to a place of more stability. Okay? There are some elements on the chart that didn't seem to have to do anything to get to a stable position. Does anybody know the ones that were especially stable?
The gases.
Those noble gases, right, okay? All of the data showed, I mean, it's very, very hard to get them to react. We have forced krypton and xenon. I don't know about the last one, but I know, but krypton and xenon, we have forced them to react, but it takes a lot of energy to do it because we're taking them out of a very stable energy place. Does that make sense? Okay, so all that to say, when we write our electron configurations, we start with the energy levels and the energy sublevels and the energy orbitals. We'll actually get to all of that have the lowest energy first. Okay? Does anybody know the very first place to start?
Uno.
Uno. One what?
S.
1s. Okay? So, in the 1s position, does anybody know how many electrons can fit in an s? 2. Good remembering. And I'll review this. Don't worry. Those of you who are like, how do they know that? Okay, we'll put some logic to it all. So that's the lowest energy place that electrons can be in an atom. 1s2. Okay, so we've got 2 out of 11 down. Okay? Who can tell me the next place to put them? 2s. And does a 2s have more or less energy than a 1s?
Same.
Nope, it has more. Okay? The first energy level, if we were to make like a diagram, is this still on the screen? Okay, for energy, the 1s would be here, the 2s would be a little bit higher. It's the second energy level. Okay? All right. Now, how many electrons can fit there? 2. But this tells us why we filled up the 1s before the 2s. If they were the same energy, it wouldn't matter which we filled first. Okay? All right. What comes after 2s?
2p.
Ooh, good remembering. 2p. And if we were to track it on our energy graph, the 2p would be right here. How many electrons can fit in a 2p?
6.
Wow, there's a lot more room in a p sub level. So 6 can fit. So how many have we accounted for so far?
4.
2 and 2 is 4, plus 6 is 10. We're almost there. We had to shoot. We had to go to 11. Okay, what comes after 2p? 3s. Very good. And A 3s can hold how many electrons?
2.
It can hold 2, but for sodium, how much does it need to hold?
1.
Just 1. And if we were to track the energy, the 3s would go right here. Okay? And if you count them up, 2, 2, 6, and 1, that is your 11 electrons. So this is sodium's electron configuration. Does that make sense? Okay. Now, how many of you, did anybody write a shortcut? Okay. All right. Leora, what did you write for your shortcut?
I put neon in brackets, and then I wrote 3s with the 1.
Perfect. Very, very good. How many of you really don't know how to do a noble gas shortcut? Well, I could. Some of you are raising your hand. Some of you are giving me a face like, well, okay. So let's do this. If I had asked you instead of writing sodium to write the electron configuration of neon, okay, let's look on the chart. Find out where neon is. How many electrons do we have? Okay. All right. So there's 10 electrons in neon. Very good. Okay. And so now let's track them. Okay. Let's go back. So where's the first place that they go? 1s2. Now where? 2s2. Now where? 2p6. Are we done? Yes. 2 and 2 is 4 plus 6 is 10. And if you look, isn't this starting part of sodium exactly what we wrote for neon? Okay. So that's why Leora knew to just put neon's configuration and then a 3s1. So you are allowed to use this shortcut, but we can only use noble gases because those kind of complete an energy level, and then we go on to the next one. So you can't, like for magnesium, you can't do sodium and then one more. Okay, we're always just going to use a noble gas.